One idea to get at convergence or divergence that we actually used once before when we talked about the harmonic series is just changing the individual terms of the series to make them bigger or smaller, right? So the intuition behind this is if you have a series and all of your series, all of the terms in your series are smaller than some other series and that one converges, then your series must converge, right? If you have a convergent series and you make the terms smaller, it can't blow up to infinity anymore. It has to converge, right? And then vice versa, of course, if your series is bigger than a series that diverges, then when you add yours together, you're going to get something bigger than when you add all of the others together, but those add up to infinity, so you must add up to infinity, right? That's the idea. So let's state this test carefully. This is called the comparison test, okay? So the statement is, if you have a series that is between 0 and, if you have terms that are always between 0 and some other collection of terms, b's, for large enough n, and the series of the b's converges, then the series with the a's converge. And conversely, if the terms in your series, a sub n, are greater than or equal to the b sub n's for large enough n, and the series with the b's diverges, then the series with the a diverges. Okay, so let's look at the proof of this. And we're going to prove this just by looking, using the partial sums. Okay, so the partial sums for the A series, I'm going to call those partial sums S, and the partial sums for the T series, I'm going to call T. Sorry, the partial sums for the B series, I'm going to call the T's. So T sub k. Oh, this should be a K right here. Okay, so and actually we want to start at wherever our A's are, wherever these inequalities become valid. Okay, so I'm going to start at n. So k has to be bigger than or equal to capital N here. Okay, so first for the first case, let's suppose that our terms, the A's, are trapped between 0 and the B's. So 0 is less than or equal to A sub n, which is less than or equal to B sub n. So that means so let's look at the kth partial sum of the A's. And this is a modified partial sum because we're starting at position capital N. So that's going to be A sub capital N plus A sub capital N plus 1 plus and so on all the way out to A sub k. Okay, well, each one of these A's is less than or equal to the corresponding B, right? So less than or equal to A sub n is less than or equal to B sub n. A sub n plus 1 is less than or equal to B sub n plus 1, and so on, out to A sub k is less than or equal to B sub k. But that means that when you add all of the b's up, you have to get something bigger than when you add all the a's up, right? Because the b's are bigger than the a's. So that means that T sub k has to be bigger than S sub k, right? So we have, also all of these are greater than or equal to 0, right? That's something that we assumed, and so that means that S sub k also has to be greater than or equal to 0. So now we have 0 is less than or equal to S sub k, and that's less than or equal to T sub k. Now when we take the limit as n goes to infinity, right? Well, if you add 0 together infinitely, or the limit of 0 is just 0. The limit of T sub k, well, that's the sum from n equals capital N to infinity of B sub n. And remember, we assumed that this converges. And we're asking the limit of the S sub k, that goes to the sum from capital N to infinity of A sub n, right? So the sum from n to infinity of a sub n is between 0 and the sum of the b's. And we know the sum of the b's converges. So now we're in a situation we've been in before, right? For this series, the partial sums, the sequence of partial sums increases because all of the a's are positive, or non-negative, and is bounded. Because it's bounded above by whatever the b's add up to. Okay? So that means that the sum from n equals capital N to infinity of a sub n converges. So the entire sum converges, right? If the tail converges, the entire series will converge. Okay. So that's just for the case where the a's are smaller than the b's and the series with the b's converges. You can see that the second case of this comparison test, where the a's are bigger than the b's and the series with the b's diverges, that's going to be the same argument, but just with all the inequalities turned around and convergence replaced with divergence. So I won't prove that one separately, but you can see that it's going to work out the same way. All of the partial sums for the a's are bigger than the partial sums with the b's, but the partial sums with the b's go to infinity, and so the partial sums with the a's have to be bigger than that, so they also go to infinity, so it diverges. So I won't write that out, but hopefully you get the idea.